Welcome to the Explainer. So, have you ever stopped to wonder how the spinning motion of massive macroscopic objects, like, say, a swirling galaxy or a pirouetting dancer, could possibly be governed by the exact same fundamental rule as the invisible microscopic particles making up your own body? It sounds wild, right? But today, we're unraveling one of the most beautiful and honestly unbroken laws in all of physics: angular momentum.
Okay, let's dive right into this. We'll start with the familiar sight. Imagine a figure skater spinning on the ice. You know the move. When they pull their arms in tight to their chest, they suddenly spin much, much faster. Or think about how planets maintain their sweeping elliptical orbits around the sun without just flying off into deep space. This isn't just magic, and it's definitely not arbitrary. Before we hit you with any of the math, I want you to anchor this physical intuition in your mind. Something really profound is being conserved in these spinning motions.
Here's our roadmap for this explainer. First, the mechanics of spinning. Then, defining angular momentum. Third, the rule of conservation. Fourth, the hidden symmetry. And finally, the quantum spin. We're zooming all the way from classical mechanics down to the mind-bending rules of the quantum universe, so let's get started.
Section 1. The mechanics of spinning.
To really grasp this, we need to establish the absolute fundamental intuition of what happens when objects spin. And if you understand how objects move in a straight line, you're literally halfway there. Just look at this direct parallel. In standard linear motion, Newton's second law tells us that a force changes linear momentum over time. Now flip over to the rotational counterpart. Instead of force, we have torque. And instead of linear momentum, we have angular momentum. The math just mirrors itself perfectly. Just as applying a force pushes a car forward, applying a torque, a twisting force, changes an object's angular momentum. Simple as that.
Section 2. Defining angular momentum.
So what exactly is this angular momentum quantity? Let's introduce the formal mathematical definition. But here's the catch. Unlike linear momentum, which just inherently belongs to a moving object, angular momentum must always be defined with respect to a specific point, like an origin on a graph. Saying a particle has 2 units of angular momentum is completely meaningless unless you tell me where you're measuring it from. And this brilliantly illustrates the math behind it. What you're seeing here is the cross-product formula. L equals r cross p. R is the position vector from your origin point to the object, and p is the object's linear momentum. Because it's a cross product, the magnitude heavily depends on the angle between those two vectors. If an object is moving directly toward or away from your origin point, the angle is 0, and its angular momentum relative to you is exactly 0. But the more perpendicular its motion is to your line of sight, the higher the angular momentum.
Now, because we're dealing with 3D space, this cross product gives us a vector. But which way does the angular momentum arrow actually point? Well, I want you to try this right now. Seriously, take your right hand, point your fingers in the direction of the position vector r. Now curl those fingers toward the direction the object is moving, vector p. Look at your thumb. It sticks straight out, completely perpendicular to the plane formed by your fingers. That is the true direction of the angular momentum vector. It points perfectly perpendicular to the plane in the motion. Pretty cool, right?
Section 3. The rule of conservation.
Now we arrive at the core of the magic. We know that torque changes angular momentum. But what happens to a spinning system when there is absolutely 0 net torque applied from the outside? Well, this brings us to a massive, foundational concept in all of physics. Listen to how physicist Dan Kleppner describes this. We conclude that conservation of angular momentum is an independent physical law, and until a contradiction is observed, our physical understanding must be guided by it. I absolutely love this quote because it highlights that this isn't just some convenient math trick. The fact that angular momentum doesn't change when net torque is 0 is an absolute fundamental law of our universe. It literally dictates the motion of galaxies, stars, and planets.
Let's actually apply this law to a real-life astronomical example. Imagine a meteor flying through space, grazing past the Earth in a massive, sweeping arc. If we completely ignore air resistance and only consider Earth's gravity, is the meteor's angular momentum conserved around the center of the Earth? Let's check the physics.
So, the crucial point here is the relationship between the vectors. The gravitational force on the meteor pulls directly toward the center of the Earth, but the position vector points directly away from the center of the Earth to the meteor. These two vectors are perfectly anti-parallel. And as we learned just a minute ago, the cross product of parallel or anti-parallel vectors is 0. That means gravity creates absolutely 0 torque on the meteor relative to the Earth's center. Because torque is 0, the meteor's angular momentum remains perfectly constant throughout its entire terrifying flyby.
Section 4. The hidden symmetry.
We've seen how conservation works in practice, but we really have to ask a deeper question here. Why does this conservation law exist in the first place? Like, why does the universe care about keeping angular momentum constant? The answer lies in something incredibly profound. Enter Noether's theorem, devised by the brilliant mathematician Emmy Noether. Her theorem states that every continuous symmetry in the universe has a corresponding conservation law. So conservation of angular momentum fundamentally arises from the universe's rotational symmetry. Think about it. The laws of physics don't suddenly change just because you rotate your perspective or your laboratory 90 degrees. Because the universe has no preferred direction or angle, angular momentum must mathematically be conserved. It's literally a direct byproduct of the geometry of the universe itself.
And here's a fantastic little detail. We used the right-hand rule and the cross product earlier to define angular momentum, right? Well, the cross product only mathematically works in three-dimensional space. But Noether's symmetry? It doesn't care about our 3D limitations. Through her theorem, angular momentum can be defined using an anti-symmetric matrix, meaning this magnificent conservation law holds true mathematically whether you're in 2 dimensions, 3 dimensions, or even an 11-dimensional string theory universe.
Section 5. The quantum spin. Let's move to and see how this builds in the micro world of quantum mechanics, where angular momentum takes on a completely different, almost alien personality. In classical physics, our figure skater can spin at literally any arbitrary speed. Their angular momentum can be a smooth, continuous spectrum of values. But in the quantum realm, particles can only possess angular momentum in strict, discrete increments. There's no continuous speeding up or slowing down. It's kind of like if you could only drive your car at exactly 10 miles an hour or exactly 20 miles an hour, but never 15. The angular momentum is strictly quantized.
Now, what's really interesting about this slide is how we visualize these discrete states. Instead of a vector that can point smoothly in any direction like a classical spinning top, quantum particles have a finite, limited set of allowed angular momentum angles relative to an axis. These visuals show the only allowed, strictly quantized orientations a particle's angular momentum can take. It's highly restricted, and yet it's perfectly ordered. In the quantum world, total angular momentum is actually made of 2 parts. You have orbital angular momentum, which is somewhat analogous to our classical spinning, but then you have something called spin. And this intrinsic spin has absolutely no classical equivalent. An electron doesn't actually spin like a tiny baseball. Rather, spin is just a fundamental built-in property of the particle itself, just like its mass or its charge. Electrons and quarks have a spin of 1/2. The mysterious Higgs boson, it has a spin of 0. It carries no angular momentum at all. And yet, this intrinsic quantum spin dictates the magnetic properties of all materials and literally prevents matter from collapsing in on itself.
We've gone all the way from the ice rink to the edges of the galaxy, all the way down into the fundamental properties of the electron, and they are all bound by the exact same rule, born from the simple fact that the universe doesn't care which way you're facing. So I'll leave you with this. If the universe's mathematical symmetries elegantly govern both the macroscopic spin of a galaxy and the intrinsic, discrete spin of a quantum particle, what other invisible connections are out there, just waiting to be found? Keep exploring, and thanks for joining me on this explainer.